Your pension, your life insurance, these are some of the biggest, most important financial promises you'll ever rely on. Today, we're going to pull back the curtain and go inside the machine to see how those promises are actually built to last. I mean, really think about that for a second. Some company takes your money today, and in return, they give you a rock-solid promise to pay you or your family a whole bunch of money decades from now. How in the world is that possible? How can they be so sure that money will actually be there? And that, right there, is the million-dollar question. It's all about pricing a promise that has to survive, decades of unpredictable stuff. Market crashes, inflation, you name it. How do you put a price tag on a future you can't possibly know? So what's the secret? Well, it's not like they're just crossing their fingers and hoping for the best. It's a highly structured system, one that's designed from the ground up to manage all that uncertainty. And the architects of this whole system, they're called actuaries. And the engine that drives this whole thing is something called the actuarial control cycle. You can think of it as the master blueprint, the operating manual for making and keeping a long-term financial promise. Now, the first thing you probably notice here is the shape. It's a loop. It's a circle, and that is the absolute key. This isn't some set it and forget it kind of plan. No way. It's a continuous cycle of designing the promise, checking in on it, and constantly adjusting to make sure it stays on track. So, let's break this cycle down. It's got 4 main stages. First, you have to specify the problem, like what exactly are we promising here? Then, you develop a solution, which means designing the actual product and figuring out the price. Then, and this is so important, you monitor the experience. You're constantly comparing what's actually happening to what you thought would happen. And wrapping around the whole thing is professionalism. For this explainer, we're really going to zoom in on that second stage, developing the solution. All right, so this is where it gets really interesting. This stage is where it kind of looks like magic. I mean, to design a product that can last for 40 years, you literally have to simulate those 40 years. You have to build a model of the future. The best way to think about it is like a financial flight simulator. Before a brand new airplane ever takes off, engineers test it in thousands of different simulations, right? They throw everything at it. Terrible weather, engine failures, you name it. Well, actuaries do the exact same thing for financial products, running them through all sorts of economic scenarios to see if they can survive a storm. Okay, so the first tool they pull out of the toolkit is something called a deterministic model. This is like running just one single, very specific flight path in that simulator. The definition here says it all. In a deterministic model, you lock everything in. You say, okay, for this one test, let's pretend inflation is exactly 2%, and our investments earn exactly 5% every single year for the next 40 years. You plug in those fixed numbers, you hit go, and you get one single, totally predictable result. And here's where you see the big trade-off. On the one hand, the deterministic model is simple, it's fast, it's easy to explain. But its weakness is a big one. What if you never test for the one scenario that could blow everything up? On the other hand, you have stochastic models. These are way more complex. They're like running thousands of flight simulations all at once, with different weather patterns every time. They give you a much better sense of all the possible outcomes, but man, they are a lot more expensive and complicated to build. Okay, so you've run your simulations, you've got a pile of results. Now what? How do you actually judge those results? How do you decide if the product you just modeled is a good idea or a total disaster waiting to happen? Do you need a scorecard, right? You need some kind of clear, simple metric that tells you if you've designed a profitable product or if you need to go back to the drawing board. And the official term for that scorecard is a profit criterion. It's a tool specifically designed to cut through all that data and give you a straightforward answer, is this thing going to make money or not? So a really common one they use is the discounted payback period, or DPP. It asks a pretty simple question, how long until we break even? But there's a super important twist. It discounts future profits. It recognizes that a dollar you might make 10 years from now is worth less than a dollar you have in your hand today. So the DPP tells you the real time-adjusted break-even point. But, every single one of these metrics has a hidden catch. The DPP is popular because it's so simple. Everyone understands a 7-year payback period. But, and this is a huge but, look at its disadvantage. It completely ignores any profits you make after that payback period. You could be leaving enormous profits on the table in year 8 and beyond, and the DPP wouldn't tell you. The other metrics try to fix that, but they bring their own set of problems. So we have this amazing control cycle, these powerful simulation tools, these clear scorecards. It all sounds pretty foolproof, doesn't it? Well, not so fast. Here comes the big reality check. Every single one of these tools has its limits. I love this quote from the source material because it just hits the nail on the head. It doesn't matter how fancy your model is. At the end of the day, it's built on a foundation of assumptions about the future. And those assumptions will almost never, ever be perfectly correct. And why is that? Well, for one, every model is basically driving while looking in the rearview mirror. It's trained on what happened in the past, but the future rarely plays by the same rules. And they can't predict those truly out-of-the-blue black swan events that just change everything overnight. Ultimately, this whole system isn't designed to eliminate uncertainty. It's designed to manage it. Which brings us all the way back to our first question. If every model is flawed, how safe are these promises? Well, the answer is that they're safe not because someone has a perfect crystal ball. They're safe because the system isn't built for perfect prediction. It's built for survival. It's a living, breathing process of monitoring and adapting. The real promise isn't that they know the future, but that they have a really, really good plan for when they inevitably get it wrong.